Hello everyone, you're welcome to this channel. Today we shall be looking at another numerical method of analysis in engineering mathematics. So in the last tutorial, we look at Newton-Raphson numerical method as well as fixed point iteration. Today we shall be looking at secant method. Secant method is a method that looks like Newton-Raphson in no ramification. For those who try to avoid finding derivatives in engineering mathematics, then secant method is the right choice for you. So let's look at how secant methods look. You remember Newton-Raphson? To find the next x, you find it like this. Function of xn divided by derivative of the function of xn. To use secant, you only replace this with algebraic difference instead of finding the derivatives. So as a result, we have xn plus 1 equals to xn minus function of xn divided by a replacement for the derivative now. So it's algebraic difference of the function minus the function at initial position divided by the difference in the position. So in essence, we have the second method looking like this. So as a result, to find the xn, the next x, we are going to be needing the last x as well as the previous one before that, xn minus 1. So it means instead of the single guess that we made during the Newton-Raphson and fixed point iteration, we are going to be needing two initial guesses, x0 and x1. x0 and x1. So let's look at an example. Find the approximate root of this function using secant method. So we use this function exactly as it is when we were treating the Newton-Raphson and fixed point iteration. So let's see how it looks. So we follow the same pattern or similar pattern as before. So initial guess. So but in this case, we are going to find two initial guesses. Two initial guesses. So you remember when we follow the procedure we use, where we demonstrated, then we find our x to be 1.5. But now we need two initial guesses. Let's take the first one as 1.4 and the second one, which is what we chose then, as 1.5. So these are the two initial guesses. So to find the next x, which will now be x2, is going to be x1. Call this equation is going to be x1 minus function of x1, x1 minus x0, and function of x1 minus function of x0. So that's going to be 1.5 minus function of x0, x1 rather, which is now this, 2 times 1.5 cube minus 2 times 1.5 minus 5. Then xn minus x1, that will be 1.5 minus 1.4. So 1.5 minus 1.4. Then divided by the function of x0 minus function of minus function of x0. So divided by function of x1, which will be 2 times 1.5 cube minus 2 times 1.5 minus 5, minus function of x0, which will be 2 times 1.4 cube minus 2 times 1.4 minus 5. When we evaluate that, we are going to have something like x2 is now equal to 1.617702. So let's proceed to find x3. To get our x3, is going to be equal to x2, which is 1.61. So our former x2 now comes in, and the previous one will now be 1.5. So 1.617702. So remember now our x2 is 1.617702, and our x1 is 1.5. So those are the two x's we are going to use now. So to get our x3, minus 2 times 1.617702 cube minus 2 times 1.617702. So remember, we are still evaluating this function x 2x cubed minus 2x minus 5. So minus 5. Okay. Then x minus x minus 1, that will be 1.617702 minus 1.5. Everything divided by function of xn, which will be 2 times 1.617702 cube minus 2 times 1.617702 minus 5. Then minus function of xn minus 1, that will be 2 times 1.5 cube minus 2 times 1.5 minus 5. So when we evaluate this, we are going to get x3 equals to 1.599309. When we continue the iteration, we are going to have something like this. So in which case our x1, x2 is this, x3 is this, x4 will be 1.600 and x5 will be 1.600 as well. So that means by the time we get to x5 or step 4, when we start counting what we have been iterating, n1, n2, n3, n4. So by step 4, the convergence has taken place. So when we compare this to Newton Raphson, in Newton Raphson, by step 3, the convergence has taken place. While fixed point, the convergence took place at step 4. So that shows that our second method is also equally reliable. So thank you for following. Now, another important numerical method we are going to be looking at is interpolation. Interpolation. We encounter this regularly in engineering. So interpolation has to do with finding a missing value within a curve or line. So let's look at this line. So we can have a straight line as a function, or we can have curve like this. So let's assume in this straight line, we know this point, which is y naught, and the x there is x naught. We also know this point, which is y1, and the x there is x1. But we don't know this point y in the middle, and the corresponding x is known, which is x. So we are looking for the point y. So since we know y naught and y1, so we try to interpolate. So this is a linear interpolation because it occurs on a straight line. And at times too, we can have a curve. We can have a curve where we know, let's say here we know we have the y naught and x naught, and here we have the y1 and x1. So around this point, we are looking for y corresponding to x. So we are going to look at different methods to tackle this. For a straight line, often we use a linear interpolation. Linear interpolation, whereby we can say our y, which is this point, y minus y naught over y1 minus y naught equals to x minus x naught all over x1 minus x naught. This is a linear interpolation. If we apply the same thing in a curve, we are going to have serious error. So this is suitable for only straight line interpolation. But if we apply the same thing as into a curve, we are going to have serious trouble because we are going to have a wide margin of error depending on how the function looks like. So let's look at a very reliable method to do that. So we have Lagrange interpolation, in which case the linear type is expressed like this, much similar to what we have used in the linear interpolation above, or the quadratic type when we have a curve is expressed like this. Let me show you how this quadratic type operates. So when we have a quadratic type or a curve that is non-linear type, simple. So in non-linear type, when we have a curve like this, and we have y naught here corresponding to x naught, we have y1 here corresponding to x1. So in this case, we are now looking for y here on a curve corresponding to x. So Lagrange method states that you take a particular point for reference. Let's assume we take x naught and y naught for reference. So that means all other points will be subtracted from x and x naught, y and y naught. So let's see how it will look. So to find this y, Lagrange states that it's going to be equal to x minus x1 all over x minus x1 all over x naught minus x1, since we have taken our x naught as reference. So multiply by the reference, which is the y naught here. So plus, we have to take x1 now as reference while we remove this x naught from reference. So in that case, we are going to subtract all other points from x naught, from x and x1. So it's going to be x minus x naught all over x1 minus x naught. So multiply by y1, which is our reference point. So when we evaluate this, we are going to get accurately our unknown point. So let's see a case whereby we have more than 2 points. So in this case, we have y naught corresponding to x naught. We have y1 corresponding to x1, and we have y2 corresponding to x2. So this corresponds to, so we are looking for this y corresponding to x. So Lagrange say that once you take x naught as your reference, then you subtract x1 and x2 from x and x naught. When you take x1 as your reference, you subtract x naught and x2 from x1 and x. So let's see. So to find y is going to be equal to, let's take x naught as reference now. So that means we subtract all other points from x and x naught. So that means x minus x1 all over x naught minus x1 multiplied by x minus x2 all over x naught minus x2, everything multiplied by y naught, since our y point x naught is our reference. Then plus, we now take another reference now, x1 now and y1 are taken as reference. So that means we subtract all of that point from x and x1. So it's going to be x minus x naught all over x1 minus x naught, x minus x2 all over x naught minus x2 multiplied by y1. x1 minus x2 multiplied by y1. Then we continue. We have plus x minus x naught. We are not taking x2 now as reference, all over x2 minus x naught multiplied by x minus x1 all over x2 minus x1 multiplied by y2. So all addition of this will give us an accurate y. So it continues. Even if we have more than 3 points, 4 points, the principle remains the same. So let's look at an example here. So we are looking for the point 2.7. We are trying to find 2.7 using Lagrange interpolation. So we know this is our x naught, this is our x1, and this is our x2. So we are looking for x here. The x is here, which is 2.7 we are looking for, and that corresponds to our y. So when we look at this, we have our y naught here, y1 and y2. So just as I explained, it's going to be y equals to what is our x now? 2.7. 2.7, we are taking our reference here now at x naught. So 2.7 minus we come to that means we subtract this and this from the two of them, x and x naught. So 2.7 minus 2.5 all over x naught, which is 2 minus 2.5, multiply by 2.7 our x again minus 3 all over x naught, which is 2 minus 3, multiply by y naught now, which is 0.6932. 0.6932. So then plus we take this now as our reference point. So we remove the x naught. So it's now going to be 2.7 minus 2, which is x naught, all over 2.5 minus 2. Then 2.7 minus 3 all over 2.5 minus 3, multiply by y1 now, which is 0.9163. Then we make this as reference now. So that means we have now 2.7 minus 2 all over 3 minus 2. Then 2.7 minus 2.5 all over 3 minus 2.5. Everything multiplied by y2, which is 1.0986. So when we evaluate this, we are going to have, when we have evaluate that, we are going to have our value to be, so our y equals to 0.99411. So if you look at 0.99411, you will see that it falls in between 0.91 and 1.09, which makes our result very reliable. So we can go on and on to solve for other form of cubic interpolation as well, where we have we have 3 points or 4 points. So instead of 3 points in cubic in a quadratic type. So in that case, we are going to be subtracting each of them. So when we take this as a reference, we are going to subtract. So our x, which we are looking for, is at 0.6. So x 0.6 is somewhere here. This is our x here. So that means we are looking for y here. So that means when we take this as a reference, we are going to subtract this, and this from x and this, and multiply by this. When we take this as reference, we're going to subtract this, and this from x and this, and we multiply by this, and so on and so forth. So we continue like that. We are going to find the Lagrange interpolation very, very interesting. Thank you for listening, and remember to subscribe to this channel and post any comment that you may have in the comment section. Thank you.